Have you ever found yourself lost in deep thoughts about what nothingness truly is? Today, we're going to explore mind-blowing questions about nothingness and seek all the answers. Does nothing exist, or is there only quantum foam? Does the Schwinger Effect demonstrate something from absolutely nothing? Can quantum fluctuation potentially create a universe from nothing? How does Hawking radiation convert vacuum energy into detectable matter? How did inflationary cosmology turn nothing into a universe brimming with galaxies and stars? How does the Casimir effect manipulate nothing to produce measurable forces? Can the concept of zero-point energy redefine our understanding of a true vacuum? How vacuum decay would destroy the universe? Let's delve into the answers to these questions with a comprehensive scientific perspective. The question, what is nothing, has perplexed philosophers since the era of the ancient Greeks, who engaged in extensive debates about the nature of the void. They devoted considerable time to discerning whether nothing could be considered as something. Though the philosophical aspects of this inquiry hold some allure, the query has also captured the attention of the scientific community. If scientists were to extract all the air from a container, creating an ideal vacuum free from matter, it might initially seem that they've created a space devoid of anything. The removal of matter leaves only energy, akin to how solar energy traverses the vacuum of space to reach Earth, and external heat could potentially enter the container. Thus, the container wouldn't be completely empty. Yet, consider if the container were also brought down to the lowest conceivable temperature, absolute zero, preventing it from emitting any heat. Additionally, imagine if the container were insulated against all external energy and radiation. It might then appear that the container truly contains nothing. However, this is where the nature of nothing becomes paradoxical. Quantum mechanics introduces the concept that even in such a void, fluctuations occur in the quantum field, which implies that nothing is never truly empty. These fluctuations can momentarily bring particles and their antiparticles into existence before they annihilate each other, demonstrating that even the most perfect vacuum is not devoid of activity or existence. Thus, the scientific notion of nothing is far from the intuitive understanding of it. Quantum mechanics presents puzzling concepts, like particles being waves and cats being simultaneously alive and dead. Among these, the Heisenberg uncertainty principle stands out, typically explained by the inability to perfectly measure both the position and velocity of a subatomic particle at the same time. This principle extends further, stating that energy measurements cannot be perfectly precise, and that accuracy worsens with shorter measurement durations. At nearly zero time, the precision of measurements becomes infinitely poor. These principles introduce challenging implications for understanding the concept of nothing. For instance, attempting to measure energy at a point where it should be zero often results in non-zero measurements. This isn't just a problem of measurement, it reflects a reality where, for brief moments, zero does not consistently equal zero. When this surprising fact, that expected zero energy can turn out to be non-zero in short intervals, is combined with Albert Einstein's equation, energy equals mass times the speed of light squared, it leads to an even stranger outcome. According to this equation, energy and matter are interchangeable, which, when aligned with quantum theory, suggests that in a space thought to be completely empty and devoid of energy, there can be brief fluctuations to non-zero energy levels, allowing for the spontaneous creation of matter and antimatter particles. At the minuscule quantum scale, what appears as empty space is far from vacant. It is, in fact, a bustling scene, where subatomic particles continuously pop into and out of existence. This spontaneous generation and annihilation of particles is somewhat akin to the lively action of foam on a freshly poured beer, where bubbles form and burst, an analogy that has led to the term quantum foam. Quantum foam isn't merely a theoretical construct. It manifests in observable phenomena. One such evidence emerges from measuring the magnetic properties of electrons. Without the effects of quantum foam, electrons would exhibit a predictable magnetic strength. However, actual measurements reveal that their magnetic strength is slightly greater, about 0.1% higher. When adjustments for the quantum foam's impact are considered, theoretical predictions and experimental results align with remarkable precision, down to 12 decimal places. Another proof of quantum foam's existence is observed through the Casimir effect, named after the Dutch physicist Hendrik Casimir. This phenomenon can be demonstrated by positioning two metal plates extremely close to each other in a perfect vacuum, just a fraction of a millimeter apart. According to the concept of quantum foam, the vacuum between the plates teems with subatomic particles flickering in and out of existence. These particles exhibit various energy levels, typically low, but occasionally higher. In quantum mechanics, particles also behave like waves, which possess wavelengths. Outside the narrow gap between the plates, waves of any length can exist freely. Inside the gap, only waves shorter than the gap can exist. Longer waves are excluded. This creates a discrepancy in particle types between the inside and outside of the gap, resulting in a net inward pressure. Therefore, if quantum foam is real, this pressure should push the plates together. Indeed, experiments have conclusively demonstrated this effect, affirming that the plates move due to the pressures exerted by quantum foam. Thus, the concept of quantum foam validates the intriguing idea that in the realm of quantum physics, nothing is truly something. You can actually create matter from complete nothingness, a concept that is both mind-blowing and well documented through various experiments in the past. This not only intrigues, but also reshapes our understanding of the universe's formation, suggesting that there didn't need to be anything before the universe to bring it into existence. Firstly, based on the iconic formula by Einstein, energy equals mass times the speed of light squared, we understand that matter can be converted into energy and vice versa. For example, our sun, which engages in fusion, operates under the principle that mass is converted into pure energy. Theoretically, having enough energy confined in a small space can result in the creation of particles. This is often demonstrated in powerful particle accelerators, where high-speed collisions produce massive amounts of energy. But if we were to imagine removing all particles and even all energy from the scenario, quantum mechanics suggests that the vacuum itself might not be entirely void of activity. Imagine stripping away everything from the universe, all the stars, gases, invisible entities like black holes and neutron stars, and even all forms of energy. What you'd be left with is what we might call empty space. In such a scenario, with no particles, no energy, and no celestial activity, would anything be able to form? Surprisingly, the answer is yes. Despite the apparent emptiness, space itself is never truly empty. This apparent void is permeated by quantum fields that pervade the entire universe. Within these fields, particles and antiparticles are continuously created and almost instantly annihilate each other upon interaction. Thus, even in what seems like the perfect vacuum, devoid of particles, energy, electromagnetic forces, or gravity, the essence of what might be considered absolute nothingness, there is still a dynamic play of particle-antiparticle pairs constantly emerging and disappearing. The Casimir effect provides evidence that particle-antiparticle pairs form not just in physical spaces, but even in what appears to be a complete vacuum, indicating that space is never entirely void. There is always some level of field energy present in every segment of empty space. However, due to the complexities of quantum mechanics and the principles of uncertainty, it's challenging to determine precisely how much energy is present or where it is being generated. Intriguingly, theoretical forces such as electromagnetism and gravity can operate across the entire universe without spatial constraints, further illustrating the profound nature of these quantum effects. Theoretically, under extremely strong gravitational or electromagnetic forces, these forces can tear apart certain particles, leading to the creation of new particles from what seems to be a vacuum. More precisely, if a sufficiently strong force is applied, principles from quantum mechanics can merge with Einstein's concept from energy equals mass times the speed of light squared to transform pure energy into actual matter. This concept is encapsulated in what's known as the Schwinger Effect. Essentially, this theory posits that an extraordinarily strong electromagnetic field can generate enough force to extract various particle-antiparticle pairs from the vacuum, thus creating matter. In particular, the effect predicts the spontaneous generation of electrons and positrons within these intense fields. However, this has largely remained theoretical due to the extreme conditions required to observe it. To actualize the Schwinger effect and generate these virtual particle-antiparticle pairs, specifically electrons and positrons, a tremendously powerful electric field is necessary, akin to those found around exceptionally energetic cosmic bodies like neutron stars or certain black holes. Although such conditions might be naturally occurring around neutron stars, replicating such intense fields on Earth presents significant challenges. Even with some of the most advanced reactors and lasers, achieving the necessary field strength has been beyond our current capabilities. Consequently, the Schwinger effect has remained theoretical for over 70 years, until significant developments made in 2022. In this case, the scientists employed a particularly clever strategy. Rather than working within 3 dimensions, they chose to operate in 2 dimensions, which dramatically reduced the intensity of the electric field needed to potentially observe the Schwinger effect. The experiment involved graphene, a super-strong material made of carbon known for producing numerous intriguing effects, some of which have been previously documented. Graphene, famous for being one of the strongest materials known and suggested for futuristic applications like space elevators due to its nanotube strength, played a central role. For now, the focus remains on harnessing graphene's ability to confine everything to 2 dimensions while maintaining its extreme strength and near indestructibility. In this 2-dimensional setting, the quantum particles have much less freedom, which means the required electromagnetic fields can be much less powerful. By arranging the graphene sheets into what is known as a superlattice, layers creating periodic structures, and then applying the electric field, the scientists were able to observe an interaction that mimics the Schwinger effect. Rather than generating electrons and positrons, the setup facilitated the production of electrons and empty holes, which flowed in opposite directions. This was made possible by graphene's incredible strength and its capacity to withstand powerful electric fields. While this experiment did not perfectly replicate the creation of matter from electric fields as predicted by the Schwinger effect, it arguably provided the closest approximation achievable on Earth, short of conducting experiments near a neutron star. This achievement serves as yet another validation of quantum theory and the remarkable concept that something can indeed emerge from what appears to be nothing, or in this specific instance, from a minimal electric field. This experiment not only reinforces our existing understanding of particle physics and quantum mechanics, but also integrates aspects of Einstein's theories. More importantly, it reaffirms our fundamental assumptions about the universe, that it could have originated spontaneously from nothing. Thus, it supports the idea that particles can be spontaneously created in what seems like a complete vacuum, emphasizing that even empty space is never truly devoid of activity, always bustling with the creation and annihilation of particle-antiparticle pairs. Can science uncover the origins of the universe? The Big Bang Theory, formulated by George Gamow, Ralph Alpher, and Robert Herman, retraces the development of the universe, starting from approximately 1/10,000th of a second following the initial explosion. This model charts the evolution through to the creation of the earliest hydrogen atoms and the separation of photons, a phase occurring when the universe was around 400,000 years old. This separation process led to the emergence of the cosmic microwave background radiation, which was discovered in 1965. In its early stages, the universe was a chaotic amalgam of elementary particles and radiation, all vigorously interacting. This depiction of the nascent universe has proven highly effective, pushing physicists to extend their theoretical models to the furthest reaches of time. However, a key question persists. How far back can these models accurately reach? Can they extend all the way to time equals 0, the inception of everything? Or does the concept of time become meaningless as we approach this origin? This issue is deeply philosophical, often referred to as the first cause problem. If the universe indeed had a sudden beginning, emerging ex nihilo at a specific moment, it suggests the presence of an uncaused cause, something that arises independently without preceding factors. All scientific models attempting to explain the universe's origin employ established physical laws within a defined physical framework, inherently assuming the presence of a material basis. Essentially, to witness the birth of something, one must start with an egg, prompting the question of the egg's origin. This can lead to infinite regress, a conceptual loop famously described as turtles all the way down. Therefore, constructing a viable model for the universe's origin does not resolve the fundamental question of why the universe functions as it does. While science offers extensive insights into natural mechanisms, we must recognize its inherent limitations. The enigma of why there is something rather than nothing ought to instill a sense of humility in us all. Mathematically, extending traditional cosmological models back to time equals zero results in a condition known as a singularity, where matter density and space-time curvature spike to infinity, and the spatial distance between any 2 points collapses to zero. While this might seem alarming, the occurrence of a singularity is generally regarded as indicative of the limitations of general relativity and current physics under the extreme conditions at the universe's outset. Essentially, a singularity highlights our lack of understanding at these extreme energy scales. Addressing this gap likely requires integrating general relativity with quantum mechanics, a promising avenue that many theorists are currently exploring. Quantum mechanics introduces a fundamental fuzziness to matter that becomes evident at atomic and subatomic scales. Near the Big Bang singularity, the entire structure of the universe must be analyzed through the lens of quantum mechanics, making the concepts of space and time indistinct. It's conceivable that quantum mechanics might soften the edges of the singularity, rendering it less sharp and more diffuse. Efforts to unify Einstein's general relativity with quantum mechanics have been numerous, yet their achievements have not yet matched their potential. Currently, some of the brightest minds in theoretical physics are diligently working to bridge these two foundational theories. As consensus in this field suggests, any assertion about understanding the physical conditions near the singularity should be approached with significant caution. Nevertheless, the pursuit continues. We strive to glean some understanding of the unique physics that governed the early moments of the universe. In 1973, Edward Tryon of Columbia University introduced a groundbreaking concept for applying quantum mechanics to the universe's inception. Tryon postulated that quantum uncertainty affects not only the measurement of positions and velocities, but also the measurement of energy and time. In the realm of the very small, he suggested, it might be possible to temporarily breach the law of energy conservation, even if the overall energy of the universe remains at zero. This idea isn't as outlandish as it might first appear. Consider a stationary billiard ball on the ground. It possesses neither kinetic nor potential energy if measured from the ground, existing in a zero-energy state. However, if the ball were an electron, Heisenberg's uncertainty principle comes into play, preventing precise determination of both its position and velocity at the same time. This intrinsic fuzziness means exact localization and velocity measurements of an electron are not feasible. In quantum mechanics, a true zero-energy state does not exist. Instead, there is the lowest energy state a system can achieve, known as its ground state. Given the inherent uncertainty in quantum systems, the energy of this ground state can vary. This baseline energy state, when termed a quantum vacuum, suggests that it always possesses some intrinsic structure. Hence, a completely empty vacuum, in the traditional sense of absolute nothingness, is impossible according to quantum mechanics. Within such a quantum vacuum, energy fluctuations can lead to remarkable phenomena. According to the equation E equals mc squared, which shows that energy and matter are interchangeable, these fluctuations can spontaneously generate particles of matter. This might sound unusual, but it is a regular occurrence in quantum mechanics. These momentarily existing particles, known as virtual particles, briefly appear before dissolving back into the dynamic quantum vacuum. Expanding on this concept, Edward Tryon applied the idea of quantum fluctuations to the entire universe. He hypothesized that the universe could have originated from a quantum vacuum through a bubble-like energy fluctuation. Essentially, Tryon suggested that the entire universe might be the outcome of such a fluctuation, arising from what might be termed quantum nothingness. Tryon's theory fits into models of the universe that begin from something, albeit from quantum mechanical nothingness, which is distinct from the philosophical or classical notion of absolute emptiness. In the realm of physics, the concept of obtaining something from absolute nothing, or creation ex nihilo, does not hold. Physics dictates that even the so-called nothingness of quantum mechanics has some properties and structure. Our understanding of the universe relies on two cornerstone theories: general relativity and quantum field theory. General relativity depicts the universe as a smooth continuum that warps space-time, while quantum field theory describes particles as quantized energy packets within pervasive quantum fields. Both theories are remarkably successful in their respective domains, capturing almost all known phenomena. However, a fundamental incompatibility persists between the two. Current mathematical frameworks fail to elucidate the microscopic origins of gravity or explain how discrete energy packets can distort the continuous fabric of spacetime. Despite this, it is possible to explore the behavior of quantum particles within a fixed, curved spacetime, temporarily ignoring the mutual influence between particles and spacetime curvature. This approach led Stephen Hawking, in 1974, to an extraordinary discovery. Black holes emit subtle radiation, which ultimately leads to their evaporation. Hawking radiation represents a profound convergence of gravity and quantum mechanics. A black hole is essentially a spherical region of spacetime enclosed by an event horizon, where the gravitational pull is so overwhelming that nothing can escape. Although black holes can be observed indirectly through the radiation emitted by surrounding matter, the black hole itself, as a region of space, should not emit radiation. Near the event horizon, the space appears empty. Yet, quantum physics introduces a different perspective. Quantum theory posits that the universe is permeated by fields present everywhere, even in what seems to be a vacuum. These quantum fields are subject to fluctuations, generating waves known as virtual particles, which can possess either positive or negative energy. In quantum field theory, the vacuum is a state where positive and negative energy waves counterbalance each other. Though fluctuations persist, they do not propagate in this balanced state. Real particles arise from waves that remain uncancelled, allowing them to propagate through the field. In the fabric of the universe, objects naturally move in free fall due to the curvature of space-time, following straight paths that result in falling motion. To visualize the curvature around a black hole, imagine a grid that contracts over time. An object at rest will either remain stationary or move at a constant speed relative to this grid. However, an object resisting the grid's natural movement must exert acceleration against free fall. Locally, space-time appears flat, with its curvature becoming evident only on larger scales, much like the surface of the Earth. An observer in free fall experiences nothing unusual, even when crossing a black hole's event horizon. Near the horizon, space appears empty, consistent with quantum field theory's description of a vacuum, where positive and negative energy waves are balanced. This free-falling observer perceives a vacuum and does not detect particles. Conversely, an observer hovering just above the event horizon must constantly accelerate to avoid being pulled in. This acceleration changes their perception of the waves, causing them to receive these waves at distorted frequencies. Some waves from beneath the horizon never reach this accelerating observer. As a result, while the free-falling observer sees an empty space, the accelerating observer perceives space as filled with particles because the waves no longer cancel out. The key takeaway is that the concepts of vacuum and particles are relative, depending on the observer's motion through spacetime. Different movements result in distinct experiences of quantum field fluctuations. One observer sees a vacuum while another sees particles. Near a black hole's horizon, the existence of particles is relative to the observer's frame of reference. This concept of relativity applies locally, but becomes more complex on a larger scale. In any curved spacetime, the notion of particles is relative to the observer's acceleration. Near a black hole, this relativity is pronounced. However, as one moves away from the black hole, the necessity to accelerate to remain stationary decreases, making the stationary state more natural. Hence, the particles that are relatively real near the horizon become actual particles as they move away from the black hole, leading to what we know as Hawking radiation. Hawking radiation arises from quantum fluctuations near the black hole's horizon. The vacuum can be seen as a mix of virtual particles that appear in pairs, one with positive energy and the other with negative energy, and annihilate quickly. Usually, these virtual particles cannot become real because real particles must have positive energy. However, near a black hole, the intense curvature allows a virtual particle with negative energy to exist if it is captured by the black hole, while its positive counterpart escapes. This process transforms the virtual pair into real particles, with the black hole absorbing the negative energy particle and gradually losing energy. Hawking radiation causes black holes to evaporate over time. This radiation is thermal, with a spectrum matching that of an object emitting due to its temperature. Consequently, black holes have a temperature based on their radiation energy. Larger black holes are cold and evaporate slowly, while smaller black holes have higher radiation energy and thus higher temperatures. Unlike typical bodies that cool down as they radiate, black holes increase in temperature as they shrink, a unique characteristic of Hawking radiation. As black holes lose energy, they heat up, accelerating their evaporation. However, known black holes are incredibly massive, formed from collapsing stars, weighing billions of tons. Their radiation is extremely weak, reaching only a few billionths of a degree above absolute zero, consisting of massless particles like photons. This makes their evaporation negligible, requiring an unimaginably long time to observe. Furthermore, black holes absorb cosmic microwave background radiation, causing them to grow. If the energy of this background radiation decreases as the universe expands, evaporation might eventually dominate, but this would take several billion years. Small primordial black holes formed after the Big Bang could be evaporating now, and detecting their radiation remains a hope for the future. Currently, Hawking radiation is theoretical, based on approximations and difficult to detect, yet it remains a robust prediction. Various calculations support the prediction of Hawking radiation. In 1974, Hawking examined the gravitational collapse of a star and its effects on quantum fields. Another method involves studying time as an imaginary number, a technique from statistical physics, which reveals the black hole's temperature from these loops. Experimentally, analogies help study this phenomenon. For example, fluid flows in labs mimic black hole conditions, with horizons separating supersonic and slower flows, capturing and releasing sound waves similarly to particles around a black hole. Though not perfect, these experiments align closely with theoretical predictions and yield promising results. Hawking's work has bridged gravitation and quantum physics, paving the way for unification. Hawking's formula for black hole temperature integrates constants from relativity, gravitation, quantum physics, and thermodynamics. Black hole evaporation raises questions and paradoxes in physics. Typically, knowing a system's final state allows deduction of its initial state. However, identical black holes could form from different stars, leaving no traces after evaporation, leading to the information paradox. This paradox suggests that information captured by a black hole may be lost forever. Some theorize that information remains at the horizon. Another paradox involves virtual particles at the horizon that should remain entangled, challenging current models and suggesting that some principles may need to be revised to find a unified theory. One approach is to reconsider the equivalence principle, proposing mechanisms like a firewall that violently breaks the entanglement between escaping and infalling particles. The story that the universe started from a point of infinite density and exploded into what we see today, called the Big Bang, is not entirely accurate. Instead, the universe itself expanded. Atoms formed a few 100,000 years later as temperatures cooled, and larger structures took longer. The Big Bang was a period when the universe was very hot and dense and occurred everywhere simultaneously. The Big Bang model describes the early expansion, not the universe's origin. Science doesn't yet explain how or why the universe began. The Big Bang model focuses on early events, supported by evidence observable even today, 13.8 billion years later. However, by the 1980s, this model couldn't explain why the universe is homogeneous. Why is the universe's geometry flat? And why are there no magnetic monopoles? Alan Guth and others proposed cosmic inflation, which solved these puzzles. Inflation theory explains that the universe expanded exponentially fast from a tiny fraction of a second after the Big Bang. This rapid expansion explains why the universe appears uniform and flat, and why magnetic monopoles are not observed. Evidence for the Big Bang model is now strong, with almost no scientists disputing its accuracy. However, observations in the 1970s revealed mysteries the model couldn't explain. The early universe needed specific properties to develop into today's universe, which seemed unlikely with the early Big Bang model. Unanswered questions included why the early universe was so uniform, geometrically flat, and devoid of magnetic monopoles. In 1981, physicist Alan Guth proposed cosmic inflation, solving these mysteries. Inflation caused the universe to expand exponentially fast from a tiny fraction of a second after the Big Bang, growing by at least 10 to the 78th power. This rapid expansion is allowed because Einstein's theory limits the speed of things moving within space, not the expansion of space itself. Not all physicists agree that the universe's beginning is the same as the Big Bang. Some believe the Big Bang happened after inflation, around 1/1,000,000,000 of a second later. Analogies like the universe starting smaller than an atom and expanding to the size of a grapefruit can be misleading, implying the universe has an edge, which it doesn't. The idea that the universe started from a singularity, a point of infinite density and heat, is incorrect. This notion results from mathematical extrapolation and doesn't represent a physical reality. A singularity in equations is like having a zero in the denominator. It's undefined and indicates the limits of our knowledge. The Big Bang theory doesn't propose a singularity as a physical reality. Instead, it states that the universe today is bigger and older than it was billions of years ago. Extrapolating backwards, the universe becomes smaller, denser, and hotter. At some point, this extrapolation suggests a very small, dense, and hot volume. However, our current equations fail as the volume approaches zero. Likely, different physical laws, possibly involving quantum gravity, applied at this stage. We do not yet have a theory for such conditions. Physicists are actively researching the universe's expansion. Currently, the universe is expanding, but galaxies aren't moving at the expansion rate. Instead, the space between galaxies is expanding on a large scale. Gravity ensures that on smaller scales, stars within a galaxy and nearby galaxies, like Andromeda and the Milky Way, remain gravitationally bound. Cosmic inflation caused all points within the tiny initial volume to expand, with this expansion happening everywhere in space simultaneously. There is no center of the universe. Every point moved away from every other point. During inflation, expansion faster than light speed means initially connected points moved apart and became causally disconnected, as information cannot travel faster than light. Consequently, certain parts of the universe are beyond our detection because light or gravity from them will never reach us. Inflation explains the Big Bang model's problems: homogeneity, flatness, and the absence of magnetic monopoles. On large scales, the universe appears uniform and isotropic, as seen in the cosmic microwave background, CMB, where temperature fluctuations are minimal. The universe is extremely homogeneous and isotropic, meaning it looks the same everywhere. The CMB shows temperature fluctuations of at most 0.0001 Kelvin. Before inflation, the universe might have been random, with varying densities, like a deflated balloon with wrinkles. When the balloon is suddenly inflated, wrinkles smooth out, and density differences dilute. Similarly, during inflation, the universe's tiny volume expanded enormously, smoothing out any initial irregularities and creating the uniformity we observe today. Consider the flatness problem by imagining an ant on a tiny balloon's surface, a two-dimensional world. If the balloon is small, the ant would notice the curvature and live in a closed or curved universe. However, if the balloon expands to the size of the Earth, the surface would appear flat to the ant, even though it is still a sphere on a larger scale. Scaling this up to human size, if the balloon were much larger than the observable universe, it would appear flat. Inflation stretches any initial curvature of the three-dimensional universe to near flatness. While we don't know if the universe is perfectly flat, any curvature is too small to measure with current technology. When discussing curvature, it refers to the universe's overall curvature in 4 dimensions, which is challenging to visualize. We simplify by imagining a 3-dimensional curvature of a 2-dimensional balloon's surface. A closed curvature would mean that parallel lines would eventually converge, similar to parallel lines on a balloon's surface. Inflation also addresses the monopole problem. Magnetic monopoles could theoretically form at the extremely high temperatures present during the Big Bang and should be stable enough to survive. However, inflation rapidly cooled the universe through expansion, reducing the density of monopoles to undetectable levels. If, before inflation, there were 1,000 monopoles in a cubic meter, they would be spread across a region 10 to the 78th cubic meters after inflation, making them so rare we may never detect them. The cosmic microwave background, CMB, shows that the universe is not completely smooth, exhibiting small temperature differences called anisotropies. These anisotropies don't contradict inflation. Instead, they align with the idea that small anisotropies explain the universe's structure. Before inflation, the universe was microscopic, and quantum fluctuations in matter density expanded to astronomical scales. These fluctuations led to higher density regions condensing into stars, galaxies, and galaxy clusters, explaining the observed structure in the universe. The big question is, how did the universe start and what caused inflation? This is not well understood. One idea is the presence of a scalar inflation field during the Big Bang. A scalar field can be understood through an analogy. Imagine a room with a fireplace. Every point in the room has a temperature, which is a scalar quantity with only magnitude. Now imagine the room with a giant magnet. Every point in the room has a magnetic field, which has both magnitude and direction, similar to a vector field. Magnetic and gravitational fields are vector fields, while the Higgs field and the inflation field are scalar fields, like the temperature. Theoretically, if an inflation field existed, it can be illustrated with a diagram. In the early, hot universe, the inflation field would have had a value at point A, representing a false vacuum with high energy density. As the universe cooled, the field's true vacuum, or lowest energy state, would be at point C. Natural systems tend towards their lowest energy state, so the field would want to move from A to C, but must first overcome a barrier at point B. Quantum tunneling helps the field overcome the barrier at B and drop to the lowest energy state at C. When the energy difference between A and C becomes very large, inflation starts. As the field reaches its lowest energy at C, inflation stops. This rapid process causes the exponential expansion known as cosmic inflation. Once the field reaches its minimum potential, it decays into other fields and particles, leading to the continued slower expansion described by the original Big Bang model. Inflation theory thus addresses several cosmological problems simultaneously. The Casimir force is frequently regarded as originating from vacuum energy, often cited as compelling evidence for the reality of the zero-point energy of the quantum field. However, there exists a more fundamental perspective for understanding this force. In 1948, Dutch theoretical physicist Hendrik Casimir, while working at Philips Research Laboratories in Eindhoven, investigated the properties of colloids, viscous materials composed of micro-sized particles in a liquid matrix. These properties are influenced by van der Waals forces, long-range attractive forces acting between neutral atoms and molecules. J.D. van der Waals introduced the concept of intermolecular forces in 1873, but did not provide a theoretical explanation. In 1930, Fritz London offered a quantum mechanical explanation for these forces. Casimir, collaborating with Dirk Polder, addressed a discrepancy noted by Deo Overbeek regarding the existing theory's failure to match experimental measurements on colloids. Casimir and Polder derived a simple expression for intermolecular forces that included relativistic effects, generalizing the London van der Waals force by incorporating retardation due to the finite speed of light. Casimir, intrigued by the simplicity of their results, sought a more straightforward explanation. After a discussion with Niels Bohr, who suggested a connection to vacuum energy, Casimir discovered that calculations based on vacuum energy were further simplified when considering perfectly conducting plates instead of molecules. This is the approach commonly presented in textbooks. When two uncharged conductive plates are placed a few nanometers apart in a vacuum, an attractive force emerges. Classically, with no external field other than the negligible effect of gravity, no force should be present. However, in a quantum vacuum, electromagnetic fluctuations manifest as transient electromagnetic modes, spanning an infinite range of wavelengths in free space. Between the plates, larger wavelengths are excluded. The difference between the waves existing outside the plates and those inside generates a net inward force. This force diminishes rapidly with distance and becomes significant only when the plates are extremely close. On a submicron scale, the Casimir force is so strong that it dominates interactions between uncharged conductors. At separations around 10 nanometers, approximately 100 times the typical size of an atom, the Casimir effect can exert a pressure equivalent to about 1 atmosphere. Casimir calculated the force by summing all the cavity modes. Although this sum diverges, a finite result can be obtained by considering the energy differences between plates at varying separations. While Casimir's method focused on this approach, the force is often described in terms of the zero-point energy of a quantized field in the space between the objects. The treatment of boundary conditions in these calculations has led to some debate. Casimir initially aimed to calculate the van der Waals force between polarizable molecules. This force can be computed without referencing the vacuum energy of quantum fields. In 1956, Yevgeny Lifshitz developed a general theory for calculating van der Waals forces between non-perfect conductors, demonstrating that the Casimir force is a special case. In 1975, Julian Schwinger proposed another method for computing the Casimir force without involving vacuum energy. In 1997, Steve Lamoureux experimentally measured the force to within 5% of the theoretical prediction, making it a renowned mechanical effect of vacuum fluctuations. High-energy physicists typically consider the Casimir force as originating from vacuum energy. In contrast, the condensed matter community often views it as having the same physical origin as the van der Waals force, independent of vacuum energy. The vacuum energy perspective emphasizes a macroscopic origin, while the van der Waals perspective focuses on a microscopic origin. Specialized literature often treats these approaches as complementary methods. However, the question remains, which approach is more fundamental? Recently, Robert Jaffe argued that the van der Waals force is the correct physical approach, while the vacuum energy approach is a heuristic shortcut, valid only as an approximation in the limit of an infinite fine structure constant. Hivioura Nikolaic further supported this by providing a general proof that the Casimir force cannot originate from the vacuum energy of the electromagnetic field. In his paper, Nikolaic examines the quantum vacuum approach, highlighting its relative simplicity for calculations. Nikolaic points out that electromagnetic forces are interactions between charges, but questions where these charges are located. He notes that the force arises from boundary conditions, yet the microscopic origin of these conditions is not considered. Thus, the vacuum energy explanation lacks a complete microscopic basis. He then describes how the van der Waals explanation accounts for the force. The Casimir force can be explained by the polarization of the medium, which can be traced to the microscopic polarizability of atoms. Classically, spontaneous polarization does not occur as two molecules cannot arbitrarily choose a polarization type. From a quantum mechanical perspective, the two polarizations can be viewed as a superposition, making the van der Waals force a quantum effect. The vacuum energy explanation stems from boundary conditions, specifically the absence of an electric field inside a perfect conductor due to charge rearrangement, which is polarization. The interaction energy arises from the correlation between polarization and the electric field, constituting van der Waals energy. This explanation is fundamental as it does not rely on the macroscopic dielectric constant. At a macroscopic level, dependent on the dielectric constant, this energy can be interpreted as either polarization fluctuation energy or electric field fluctuation energy. While the vacuum energy approach provides an effective microscopic description, the van der Waals approach offers a fundamental microscopic explanation. Zero-point energy, or the quantum vacuum, has long been misrepresented by science fiction and pseudoscience. Let's clarify what vacuum energy can and cannot do. It might seem astonishing that space itself could contain an energy density higher than that of an atomic nucleus. Quantum field theory predicts this, suggesting that the vacuum energy arises from the non-zero zero-point energies of the quantum fields in our universe. For the electromagnetic field alone, this energy density has been estimated to reach an astonishing 10 to the power of 112 ergs per cubic centimeter. However, observations of the universe's accelerating expansion indicate a vacuum energy density of only 10 to the power of -8 ergs per cubic centimeter. This discrepancy between theoretical and measured values is one of the most significant unsolved problems in physics, known as the vacuum catastrophe. Despite this issue, quantum field theory remains one of the most successful theories in physics due to its predictive power. Thus, the concept of zero-point energy should be taken seriously, even as we grapple with the mismatch between theory and observation. Unfortunately, the scientific legitimacy of zero-point energy has also fueled various pseudoscientific claims. If the vacuum has an energy density of 10 to the power of 112 ergs per cubic centimeter, why can't we extract infinite free energy from it? The answer lies in entropy and the second law of thermodynamics. Entropy measures the disorder of a particle system, and the universe tends towards higher entropy, meaning more disordered states. When we extract energy from a system, we harness the decay of order. For example, a car engine's piston rises when the interior chamber becomes hotter than the exterior, creating a low-entropy, special configuration. As it returns to high-entropy equilibrium, energy is extracted, propelling the car. The Casimir effect provides one way to harness vacuum energy. Bringing two conducting plates very close together excludes some virtual particles between them, lowering the vacuum energy in that region. This creates a pressure differential that pulls the plates together. While this initial pull might seem like free energy, extracting continuous energy would require separating the plates again, consuming as much energy as gained. The idea of using the reduced energy between Casimir plates as negative energy for purposes like opening wormholes or creating an Alcubierre warp field is also impractical. Another proposed use for the quantum vacuum is in propulsionless engines, such as the RF resonant cavity thruster or EM drive. This idea is flawed. Any acceleration of a real particle involves momentum transfer via virtual particles. However, transferring momentum from a real particle to the vacuum without producing another real particle is impossible. The vacuum must give up momentum to create real particles again. Despite these limitations, the quantum vacuum has practical applications. Geckos, for example, use van der Waals forces, similar to the Casimir force, to cling to surfaces. Gecko feet have microscopic hairs, called setae, which split into millions of spatula-shaped ends. These ends get close enough to surfaces to allow Casimir forces to act, enabling geckos to climb walls by manipulating quantum vacuum energy. Here's a challenge. If adult geckos can apply 200,000 setae at once to a surface, and each seta can withstand 200 micronewtons of shear force, how many geckos would you need to climb a wall using only quantum vacuum power? The universe will end, and of all possible endings, vacuum decay would be the most thorough as it could completely rewrite the laws of physics. It's remarkable that the universe is just the right size, has the right expansion rate, and particle properties to allow stars, planets, and life to exist. The habitability of our universe is largely determined by the properties of the quantum fields that permeate all space. These fields give rise to the particles that constitute all matter and forces. If these fields were different, none of the familiar structures from atoms to galaxies would exist. Most configurations of quantum fields would prevent any structure from forming. Fortunately, our universe's configuration allows for existence, but there is a mechanism that could change everything. Vacuum decay. Vacuum decay, according to some physicists, is inevitable. It can be visualized as a bubble of annihilation expanding at the speed of light, altering the nature of quantum fields as it spreads. To understand this, we first need to comprehend the quantum fields it threatens. Imagine space as being springy at every point. Consider a rubber ring at each point. Compressing the ring causes it to bounce back and oscillate around its equilibrium shape, transferring oscillations to neighboring rings and propagating waves through space. Quantum fields have different vibrational modes, similar to these rings. Each quantum field can be seen as a set of oscillations, each corresponding to a particle. A quantum field seeks its equilibrium position, where energy is minimized. Physicists represent this by plotting the energy of the quantum field versus the field value. The Higgs field may have multiple minimum values, represented as multiple dips in the energy versus field strength graph. A quantum field with multiple minima will settle into one of these dips, like a ball on an undulating surface. Moving between dips requires enough energy to overcome the barrier. In extreme energy environments like the Big Bang or near a black hole, a field can gain enough energy to move between dips. Alternatively, the Heisenberg uncertainty principle introduces fluctuations that can cause the field to spontaneously shift to an adjacent dip, a process known as quantum tunneling. For the Higgs field, theorists believe it has at least two minima with different energy values: a true vacuum, lowest energy, and a false vacuum, higher energy. The false vacuum is metastable, stable, unless the field discovers the more stable true vacuum. We don't know which minimum our universe's Higgs field currently occupies. If the Higgs field is in the true minimum, a tunneling event into the false minimum will quickly revert to the true minimum. However, if the universe is in a false vacuum, a tunneling event could be catastrophic. A bubble of true vacuum would form, expanding at nearly the speed of light and pulling the surrounding Higgs field into the true vacuum. This bubble, in a more favorable energy state, would expand rapidly, dragging the entire universe into the true vacuum. The bubble's surface tension tries to collapse it, but if the bubble exceeds a certain size, it becomes unstoppable and grows, leading to vacuum decay. Vacuum decay is a phase transition of quantum fields, similar to how boiling water transitions to vapor. This process, called bubble nucleation, involves small bubbles growing into their surroundings. Vacuum decay would fry everything. The energy released fills the expanding bubble with energetic particles. The Higgs field's energy drop reduces the masses of elementary particles, disrupting star formation, nuclear fusion, and chemistry. Life and structure as we know it could not exist. Other fields in string theory could also exist in false vacuum states, potentially rewriting physics even more drastically. Can vacuum decay actually happen? The question is whether our universe's Higgs field is in a false vacuum and whether it might decay. Precise measurements of particles like the Higgs particle and the top quark suggest we are probably in a false vacuum, though close to the boundary. Vacuum decay is inevitable if possible, with a tiny probability of occurring at any instant. Estimates range from the universe's current age to 10, followed by 1,100 zeros times its age for a single bubble to appear in our observable universe. High-energy events like those in particle colliders or cosmic rays could trigger vacuum decay, but Earth is bombarded by cosmic rays with higher energies than colliders without causing annihilation. A vacuum decay bubble is unlikely to reach us within our species' lifespan. In an infinitely large universe, vacuum decay might have started somewhere, but if it's far enough away, we're safe. Accelerating expansion could keep us out of reach of such a bubble. If vacuum decay occurs within our cosmic horizon, we won't see it coming. Let's enjoy our time, possibly billions of years, before vacuum decay potentially ends our metastable spacetime.